Okay, so good morning, everyone. You can hear me in the back okay with the mic? All right. So, first of all, reminders or a couple announcements. Remember that we do not have lecture Wednesday morning. University, in its infinite wisdom, has canceled all classes on Wednesday. This being a class, it is canceled. Along those lines, I also posted to Blackboard regarding office hours this week, just keeping with the university's calendar, all regularly scheduled office hours, Wednesday, Thursday, and Friday this week, are also canceled. And there could be some other changes just depending on people's schedules that will be posted to Blackboard as time goes on. So after today, I will see you again next Monday at this time. The last homework assignment for the class, which is going to cover this unit that we've been doing the last couple days on Google Maps, and we're going to sort of turn attention to the internet today, was posted last night. It will be due, I think I said it, a week from Wednesday, which is the 29th, at the start of class at the normal time. We'll be happy to take any questions at that time about, any questions generally about it now are fine. Specific questions at that time, and then the quiz will be the following Monday, which I think is December 4th, which is, as it turns out, the last Monday of class. Okay, so we are very rapidly approaching the end of the semester, but that homework is there for you. We'll have that final quiz, and then other than the optional final exam that we'll discuss more of that last day of classes, that's about it. We're working on grading the term papers and whatnot. I'm hoping to get the grades posted for homework 6 shortly. You might have noticed if you've logged into Blackboard this morning, the quizzes were already posted. Just as there were some issues last week with the submission of the homework on Blackboard, we had a few issues reading. We've got everything, it's under control, but it's taken us a little bit longer to sort of get everything put together because of some of those issues. But I'm hoping, we're almost done, hoping by the end of the day today I'll have those grades posted. Okay, so any questions then before we jump back in with our material? Okay, then if not, well, remember that last time we spent most of the lecture discussing, what was it? It was a particular algorithm. We spent the lecture discussing Dijkstra's algorithm, which was a way of trying to answer this driving question that we've been going at. How do we find the best route between two places? So in the context of Google Maps, we could set up a big map, and we had our little example here, if we go back a couple slides, of these 7 cities across the United States. And we were trying to figure out how do we find the best route from New York City to San Francisco. And so we could go through sort of systematically and look for best routes with the idea that we always had this table running. What was the best route we've seen so far from our starting point, New York City, to one of the other cities? And then we would systematically go through the map and consider other routes, and always keep in mind, is the new route that we're proposing better than the one we've already seen? If yes, then update our table. If not, then ignore it and move on. Okay? But at the end of the day, by the time we finished our algorithm, and I know we didn't see these slides last time because of the projector issues, but we've got them up now. By the time we get to the end then, we've discovered what's the shortest route between New York City and San Francisco based on our map. Okay? And so we then discussed a few other things and found that sort of the big thing that was going on, and maybe the major math concept involved here, isn't just an algorithm, isn't just graphs. We've already seen those and talked about those in broader contexts. But now what we're really trying to do is an optimization problem, where we're trying to say find the best of something, or the shortest path, or the quickest path, something like that, depending on how we want to measure that cost function for how do we get between the two places. Okay? And at the very end of lecture last time, we looked at a couple other applications of optimization. We're not going to repeat them here. But what I want to do today as we begin is just to consider a few different types of optimization problems. And how can we try to characterize these? Because that might influence how we go about trying to solve an optimization problem, should we see one in application. And so one key characterization we might want to look at is trying to consider, is our optimization problem discrete or continuous? Okay? Because there's going to be very different solution strategies depending on which of those labels we fall into. And the key distinction here between discrete and continuous is that we're asking, is there a finite number of possible solutions, or is there an infinite number of possible solutions? Okay, we could quabble over how we're making this difference, but we're not going to. We'll run with this for the time being. And so thinking about our map example where we had Dijkstra's algorithm, we're looking to get between New York City and San Francisco, do you think that is a continuous or a discrete problem? What do you think? I know it's early on Monday morning and I'm asking you to think. Would it be discrete? Why do you think it would be discrete? Okay, so we've got some finite possible solutions. There's only so many ways we can get from New York City to San Francisco. So we're sort of making the implicit assumption you're not allowed to loop and just sort of keep going around and around and around and around. Okay? And that's exactly right. And so there were a finite number of possible paths from New York City to San Francisco. And so this idea of Dijkstra's algorithm, when we're looking at Google Maps, this is a discrete optimization problem. Okay? There could be a very large number of possible solutions. I mean, when you think about the entirety of the Google Maps database and searching how do we get from point A to point B, is there a huge number of possible paths that it might recommend for you? Yeah, it's got to search a bunch of things. Okay? It can be a very large number, but it's still finite. There's only so many ways to get from point A to point B. Some of the other examples that we looked at last time, so we had mentioned like in automotive construction and manufacturing, optimization problems go on trying to figure out how do they design these cars so that should your car get into an accident, the cabin is protected, maybe at the expense of the engine or the trunk or other parts of the car where people don't usually reside. They would optimize the car for doing this. This is more of a continuous optimization problem. Because when you think about this, maybe what they're saying is how thick do we have to make this metal component or fiberglass component or whatever the body of the car is, how thick do we have to make it? Is there a discrete or a continuous, a finite or an infinite number of possible answers to that question? It's in principle infinite. We can make the thickness however thick we want. It could be an inch, half an inch, or somewhere in between. Okay? And so if we wanted to pose that as an optimization problem, our solution strategy would be very different than if we were trying to do our Dijkstra's algorithm when looking at the map. Okay? And so what usually happens is that discrete optimization problems usually end up involving graph theory in some way, shape, or form. Just as we saw, we had Dijkstra's algorithm. So we had, here's our map, which we've turned into a graph using some cost function to tell us how to get from point A to point B. And then once we had that, we had the graph, and we could look at how to find these routes between it. Okay, that's usually a dead ringer that we've got a discrete optimization problem. Continuous optimization problems instead usually rely on differential calculus in some way, shape, or form. I don't want to say the C word more times than necessary, and we're not going to spend a lot of time talking about those here. But you should know that they exist, and if they come up, calculus is usually going to be a tool that's going to help you out quite a bit. And if you don't like calculus, well, like I said, we're not going to need to do anything about it in this class. Okay? So, another type of characterization that we might want to look at when thinking about optimization problems is it a constrained optimization problem or is it an unconstrained optimization problem? What do you think might be the distinction between a constrained and an unconstrained problem? Boy, you're really quiet this morning. Okay, so maybe there are other conditions we have to satisfy. We're not just looking, so let's think about our Dijkstra's example. We're not just looking for the shortest path. Okay, what is the shortest path in this graph? Anybody see it? Yeah, New York City to Boston. We've got 191, let's suppose, miles from New York City to Boston. Does that tell us anything about the shortest path from New York City to San Francisco? No. So we had to put that extra constraint. When we were looking at Dijkstra's algorithm, we had to put a constraint that whatever our path was, it started at New York City and it ended at San Francisco. And of all of the paths that meet that constraint, we wanted to find the shortest one. Okay? So it turns out we had, in that sense, a constrained optimization problem. We weren't just looking for the unqualified shortest path. It would turn out if we were looking to get from New York City to Boston that that would, in fact, be the answer, but you wouldn't necessarily know that at the outset. Okay? And then the last characterization that we might want, and this applies more to continuous optimization problems than discrete, is this idea of local versus global solutions. And so you could think about if we had a function now, maybe we've got something plotted here, and we've got here on the vertical axis is what we're trying to optimize, So this would be maybe that thickness of material, although you wouldn't really have negative thicknesses. Just run with it as a figurative example. The thickness of the material in the car versus, here's on the horizontal axis, the thickness of the material in the car, and on the y-axis is, I don't know, how good that car is in a crash. Okay, however you want to measure that. You know, you can find, like, here's a minimum where we could say the car is maybe really good in the crash. Here's a maximum, maybe not so good. Another minimum, it can be good. Well, which of those minima do we want? If we want to get this function as low as possible, is any minimum good, or is there one in particular we really want to go for? We want to go for the one on the left, because that's where it has the lowest value. And what ends up happening then is we can then try to distinguish this minimum here from this one here to say this is a global minimum, which is to say over that entire function, that is the lowest value we can get. That's as small as we can get it. And so if we're really trying to engineer this the right way, that's what we should be targeting. Versus we can look over here and say, well, we've got this minimum in the function here, but it's not the smallest minimum. And so locally, it's a minimum. But when we look over the entire function, we can see there's a better option. Okay? And so in a lot of times when you're working with continuous optimization problems, this can become a big issue. And a lot of times you're going to want to find what's the global maximum or the global minimum, depending on what it is you're trying to optimize. And you always have to worry, did I get stuck in a local trap? And in some cases, maybe the local is good enough. I don't know. Again, that depends on your application. But this is just a distinction to be aware of. So when we're looking at optimization problems, we can think about now continuous or discrete. Everything we're going to see in this class, other than just some of these figurative examples, are going to be discrete. Like I said, we're not going to get into continuous stuff with calculus. Are we looking for constrained or unconstrained optima? Usually for our applications, there's going to be some constraint, because we're going to say you have to start here and end here. And then again, this local versus global is really a thing for continuous, but I wanted to show it to you and make you aware of these things so that if you're needing to do optimization in another class that you're taking or sometime out on the job, you know that this is a distinction that you might have to worry about or run into. Okay? Any questions on that before we change gears into something totally different? Okay. Then if not, we're now going to turn, this is sort of the end of our discussion on Google Maps. Certainly if you have questions, please ask or post to Blackboard or whatnot. But we're now going to turn our focus onto the last technology that we will discuss this semester. And we're going to spend today, most of next time, talking about the internet. Okay, so there's the leading question up here of any ideas on what the common theme is between Google Maps and the internet. We've actually already answered this question. It's that they're both about route finding. Okay, how do we get something from point A to point B? In Google Maps, it's how do we get you from your house to whatever the restaurant is that you want to go to while avoiding traffic. Oh, there's another constraint. Can we avoid traffic when doing it? Okay. Versus the internet now is how do we get a message from your machine, whether it's your computer, your smartphone, your tablet, whatever. How do we get a message from that to some other device that's connected to the World Wide Web? Okay. It turns out this route finding, this optimization, is going to be a similar theme, but the solution strategies that we're going to see are going to be a little bit different. So for instance, we're not going to be using Dijkstra's algorithm to try to solve this problem on the internet. Could we, in a conceptual sense? Yes. But it turns out there are practical reasons why we don't want to do that. And that's what we'll be discussing next Monday after the holiday. Today, though, what we want to do before we get to that point is try to understand what is the internet and how does it work. Because if we need to understand why Dijkstra's algorithm may not be the right way to do it, we have to understand what's going on in the technology to reach that conclusion. Okay? So maybe we'll start with the question today, what is the internet? Anybody want to take a guess? There's by no means a unique answer to this question, but there are certainly good answers. Yeah? Okay, so it's basically a connection between two devices or more devices, computers and servers and things like this. Yeah, that's basically as good of a definition as I can put up. If you're curious, it is not, in fact, a series of tubes. Does anybody know that reference? Okay, so about 10 years ago, I think it was 2007, then Senator Ted Stevens from Alaska got on the floor of the Senate and started screaming that the internet was just a series of tubes. If you want to see the video, there's a link. It's kind of funny. Also sad that he was then writing legislation about how the internet works. Anyway, So to take a definition from the BBC, and again, there's a link here if you want to see a bit more. This is a really nice reference for sort of basics of how the internet works. The internet is a global network of computers. So as we said, we've got a bunch of computers that are linked together that works much like the postal system. Just as the postal service enables people to send one another envelopes containing messages, the internet enables computers to send one another small packets of digital data. So all the internet really is this big network that moves data around. Okay? So think back to like our data transmission unit where we were looking at like text messaging. Internet is doing that at a fundamental level. Okay? Just take data from one machine, move it to another one. All right? But it gets a little bit more complicated. So again, just as a sort of a disclaimer slide, here are some other readings if you're looking for some more information on how the internet works. There are various levels of detail here. Some from like the History Channel or from BBC are pretty accessible. Some of the ones in the in-between, the second and third bullet there, maybe a little bit more detailed if you're looking for more information, but these are pretty accessible websites. Also, just want to make a note, we're going to see a lot of graphics in the coming slides. I did not make them. They were, in most cases, taken by this website for the textbook Computer Networking by Kurose and Ross. It's an interesting book, but well beyond our scope, but some of the figures were nice, and I was lazy and didn't want to redraw them. So they're there. After this slide, I'm not necessarily going to cite that book on every slide. This is that citation. If it comes from a different source, I'll cite it there. And then just the last comment, we're going to sort of do a very crash course description of how the internet works. If you want to know more information, a course on computer networking, something like CSE 310, we'll go over and basically spend an entire semester talking about what we're going to do in the next 65 minutes. Okay, so there's a lot of information that we're not going to go into as we're doing this. Okay, so the first thing we can do is try to picture the internet. What does it look like? And so sure enough, we get something on the left here that looks an awful lot like a graph. Okay, so what are the different things? So first of all, we see we've got maybe this mobile network, and here's a laptop, and we've got our smartphone and our $400,000 car that is internet enabled, wireless points. We've got different routers that we can see here, and we'll come back and talk about sort of maybe what a router is in a little bit. We've got our home network where there's a wired computer, you've got a wireless router, your laptop's floating around. Something now like the Stony Brook network where now maybe there's a sync site where there's a bunch of computers that are all hardwired into the network, but then certainly we've got laptop computers floating around. Some of you are on your phones right now. We could have actual just dedicated web servers, all now sort of behind this Stony Brook firewall and part of that Stony Brook network. And the idea is that they're all connected together. Okay, so for a couple pieces of terminology, we'll see here like this thing is labeled regional ISP, global ISP. ISP is just short for Internet Service Provider. Most of Long Island, at least for residential and a lot of commercial applications, who is the Internet Service Provider? I know none of you pay bills. Otherwise you'd know this. It's Optimum. Other major Internet Service Providers throughout the country, there's Time Warner is another one. Comcast or Xfinity is a big one, just sort of, again, depending on where you live, because they're not monopolies, they just don't compete with each other. Yay. Okay, and so what ends up coming together then is the internet is this network of all of these devices that are interconnected. We could have our computers. These are both hosts and servers. So something like the Stony Brook web server. If you go to stonybrook.edu, there's a computer, probably somewhere on campus here, that is that server that then runs the website. Okay, it's probably actually several computers, but we can get those. Any of our mobile devices that are connected through Wi-Fi to the internet are part of the internet. Routers and packet switches, which are things more sort of you don't have to think about. So does anybody have like a router in their dorm room or at home? Have you played with it at all? Okay. What does the router do? What's that? So it gives you Wi-Fi. So you've got coming in from your internet service provider, you've usually got some sort of cable. There's some wired device. But you want to have wireless through your house, so you put in a router, which then goes in. So what the router is doing is sort of allowing you to connect multiple devices through that one outlet from your cable company or from your internet service provider and sort of break it up. You can hardwire things into a router. If you go home over the holidays and look at the router, you'll see there's usually probably either 2, 4, or 8 ports for different computers that you can plug in directly. Or in this case, in 2017, most all of the routers also have wireless functionality, which allow you to then connect your phones or your laptops, tablets, whatever, using Wi-Fi. Okay? Do you ever have to think about the router when you're using the internet? Not unless it's broken. If you've got everything set up right, do you have to actually go and manually connect your router, or does your computer just do that automatically when you turn on the Wi-Fi capability? It just does that. Okay. Do you have to think about packet switches? Have any of you heard of packet switches? Okay, so that tells you how much you have to think about them when you're using the internet. Packet switches are basically other devices in the infrastructure of the internet that help relay messages between devices. Okay? There's probably packet switches up in the roof here, or up in the ceiling, so we can find some routers if we look around the room. I'm trying to see where they are in this one. Yeah, there's one sort of right up there. There's probably one over in the back, too. Okay, so we can get these. Behind those, there are going to be these packet switches helping the messages go from router to router or device to device. Typically, you as the user do not have to think about packet switches, but they are a very vital piece of the infrastructure underlying the internet that makes all of this work. And so the main conclusion is the internet has a bunch of things. If we want to think about this as a graph now, is this going to be a really big or a really small graph? It's going to be a really big graph. Okay? There are a lot of devices, millions if not billions of devices, if not more than that all have to work together to make the internet function. Okay, so which brings us to the next idea. The key to the internet really then is cooperation. So I think I've probably asked this question before, back when we started talking about digital devices way back at the beginning of the semester. How many of you have cats at home? Okay, how many of you have multiple cats at home? Okay, so there's only really one hand up, so maybe I'll ask the two of you. How many cats? You've got two? Two? Okay, so I was hoping someone would have like 9, that there was a crazy cat lady or cat person somewhere in the audience. How easy is it to get both cats to do what you want at the same time? It's impossible. Good luck getting one of them to do what you want, let alone both. Okay, so now think, as we said before, all of these digital devices are sort of like cats. And so now we've got billions, if not trillions, of digital devices, and we need them to all work together to make this happen. Is that going to just happen spontaneously? Not even close. So the idea behind the internet is we've got to get everyone to cooperate and to communicate with each other to get them to behave in the way that we want and that we can control. Okay? So what ends up happening is that this cooperation is codified, or we standardize it through what are called protocols. And there are a bunch of different protocols. We'll discuss a couple of them briefly that the internet uses to work. But at the end of the day, what you can do is think of a protocol as a language. So this is how we communicate with each other. More than that, there's sort of context, and there's politeness and courtesy that go into it as well. So for an example of maybe a protocol, email, you could think of as a protocol. Is that a way that we can communicate with each other? Yeah. So I get an email from a person. I don't know the person who wrote it. And the entirety of the message is, when are your office hours? Okay, so I look at this, and there are a couple decisions I have to make. So first of all, do I understand the message? Yeah, it's a well-put question. They're asking when my office hours are. Okay. But one thing that we might notice, although this is certainly direct, they get to the point. There's not just pages and pages and pages of text to ask this question. It has no context. I don't know who's asking this. I don't know why they're asking it. And so what I might wonder is, who are you? Okay. I might wonder, what exactly do you want to discuss? And the bigger question that I then have, if we're going to make this communication work, how do I respond? Okay. Without that context, do I necessarily know the best way to frame the response? No, I don't. And so the protocol, more than just the language, also tries to give us this context. What is it someone is trying to do? Because that might influence how we respond and then how we communicate. Okay. For an example of sort of context in literature, there's one phrase at the end of The Wizard of Oz where the wizard is almost always misquoted, and again, without context, where people say the wizard's talking to the scarecrow and says, "You don't need brains." It's a really crass thing to say, sort of even mean-spirited. For those of you that have read the book, was the wizard really a mean person? No, he's a bit inept, but not necessarily mean. Okay, so that seems a little out of character for someone who's maybe read the book. So the way the dialogue actually goes, so "I think you are a very bad man," said Dorothy. "Oh, no, my dear, I'm really a very good man, but I'm a very bad wizard, I must admit." "Well, can't you give me brains?" asked the scarecrow. "You don't need them. You are learning something every day. A baby has brains, but it doesn't know much. Experience is the only thing that brings knowledge, and the longer you are on Earth, the more experience you are sure to get. "That may all be true," said the Scarecrow, "but I shall be very unhappy unless you give me brains." So if you wanted to paraphrase the wizard, did he say you don't need brains? Yes, but you're losing a lot of context. He wasn't saying that in the sense that you're an idiot. That's not what he was saying at all. He's saying there's a difference between knowing things and being able to learn. Okay? And the fact that the Scarecrow might very well have been somewhat dim in this book doesn't mean that he was stupid. It just means he was uninformed. And that's a much easier problem to solve. Okay? So, again, there's some other literary examples here as well for how language and context work. But the idea is, if we're going to communicate, we need to agree what is it that we're going to communicate about, but then also what are the rules for communication? And how do we provide context to each other? And this is something you can imagine it's hard to do for people. Human languages are very complicated things. Anyone who's not an English native speaker that's tried to learn English can, I'm sure, attest that English is a weird language. Those of you that are English native speakers could probably attest to that too. How much harder is it then for computers? What's something people are really good at doing, per se, if they don't know what's going on in a conversation? Number one, they can ask questions and say, "Wait a second, can you repeat that?" Number two, can people infer things? Yeah. Maybe they don't infer the right thing, and that's certainly had its issues in history, but they do. Do computers usually ask follow-up questions? Not usually. Do computers infer things? Absolutely not. Or at least absolutely not yet. Those of you interested in AI, maybe that'll be different in a few years, but we're not there yet. Okay? And so there's some differences, and so when we're figuring out how do we get all of these devices to communicate to form the internet, we have to be very clear and very methodical in how we set up this communication and how we set up these protocols. Okay? And so then, as we've said, this protocol is really how we make the computers cooperate. And to quote the definition from Kouros and Ross, a protocol defines the format and the order of messages exchanged between two or more communicating entities, as well as the actions taken on the transmission and or receipt of a message or other event. So protocol has a couple things involved. Number one, what are the types of messages that we might be communicating about? You can't just sort of have open-ended communication. There's a discrete number of things we might have to communicate about. And we've described what is the format and the order of those messages, as well as how do we respond to them. Nothing is left to sort of subjectivity. You send me this request, I send you this thing back. You send me this message, I respond in this way. Cut and dry, plain and simple. No, maybe not so simple. And so an example of a protocol, we could have maybe two people on the left. One person says hi, the other person says hi. Got the time? Okay, so it's actually 9 o'clock, but 2 o'clock in the picture. Okay. Is that a perfectly valid communication between two people? Yeah. Would that be a weird communication? If someone came up to you on the street and said hi, you say hi back, and they said you have the time, and you responded 9 o'clock, are you going to walk away thinking, wow, what a creep? No, you're going to be like, okay, that person should buy a phone. Okay? On the other hand, think about if we did it the other way around. So suppose you're the person on the right there, and this person on the left comes up and says, got the time? Oh, it's 9 o'clock. The conversation ended there. Would you think they're a creep? Maybe a little bit rude that they didn't say hello first, but okay, fine. Things happen. But suppose now the conversation continued. Got the time? 9 o'clock. Hello. Now you're thinking, this person's, I'm going to walk away now. Okay? And so even though it's the exact same messages that we sent in that first order, the order matters in terms of how you respond to those messages. Exact same thing happens when we're working with computers. So now sort of for the example on the right, we might have two computers. We've got our computer on the left where we want to access a web page. And we're going to have to send a message to that web server, maybe the guy on the right there, to say, I want this web page. Can you please send it to me? Okay? And so what ends up happening is the computers are first going to say hi to each other. We've encoded politeness in the protocols. So your computer is going to send a message over to that web server saying, hi, I want to communicate with you. And that computer is going to respond back and say, hi, channels are open. For those of you who like Star Trek. Hailing frequencies open. We're then going to say, I would really like this website from you. Can you please send it to me? And that computer is going to hopefully respond back, sure, here it is. End of communication. If you want to get another web page from that computer, what are you going to have to do again? You have to say hi, starting a new conversation. But these are the protocols. These are the steps that we've put in place to make this work. Okay? And we'll talk about this in a little bit more detail. So what ends up happening is that the internet, as we've seen, is very complex, and we're going to get into some of the details here momentarily, but there are actually quite a few different protocols that work together and work simultaneously to make the whole thing work. Okay? One protocol that we'll discuss a little bit is called the Internet Protocol. It has an acronym that you might have heard of. Anybody want to guess what the acronym for Internet Protocol is? It's IP. Anybody heard of like IP with regard to internet? Okay. Like your IP address, the IP stands for Internet Protocol. Okay, so is that a protocol that's going to be important? Yeah, we're going to talk about that a little bit. Another one, if you've actually hooked up a computer network at home or played with your router, what's another acronym that you also see with IP very frequently? Anybody? MAC, okay, so the MAC is one. We're actually not necessarily going to get into MAC addresses that much. What I was looking for was the TCP. So if you've seen your computer, you've got like TCP/IP. Okay, what do you think the P stands for in TCP? It's protocol. It's what's called a transfer control protocol. And those two together are how most web interactions and internet interactions actually work. We'll discuss TCP and IP again as we get a little bit into the lecture. But these are different protocols that work in tandem with each other to make all of this communication work. Okay, so what ends up happening is that we have all these different protocols, and they all serve different purposes. And to see those, we need to make another distinction in the internet, which is to say that the internet is a lot like cakes, onions, and ogres, if you know the movie reference. It has layers. That was a Shrek reference. Okay, no one was laughing. I think it's just too early on Monday. Okay, and so the internet is divided now into several different layers that, again, all serve different purposes, and we might be using a different protocol in any given layer, again, because they've got slightly distinct purposes. So the top level layer, which is where you as the internet user exist, is what's called the application layer. And so this basically contains the programs that you actually use on the internet. So if you use an email client, that's on the application layer. If you're using a web browser, that's an application layer. Think of it, it's an application on your computer. It runs on the application layer. And this is what basically interfaces you as the user with the internet. Okay? So like you go into Chrome or Firefox or whatever your favorite web browser is. Internet Explorer is dead. And you type in a web address. What does that web browser do? Well, it goes and it sends the messages and goes through all of these steps to say, I need to get that web page. And then once it gets it, it does what? It displays it for you and renders it on your screen so that you can read it. Did you have to think about sending messages to the server or waiting for the responses or making sure that all of these niceties were followed in the computer language? No, it took care of all of that for you. That's what the applications do on the application layer. And so one example of a protocol that we'll see there is something called HTTP. I'm guessing you've heard of that before. Okay? Hypertext Transfer Protocol. Okay, so the idea that now the internet is basically made up of hypertext. All of these different web pages that we use are hypertext. And this is a protocol for transferring hypertext from one device to another. That's where HTTP comes from. If you've seen HTTPS on some websites, what's the S stand for? Security. So it's a way to add in some cryptography, thinking back to our data security unit, on top to make the communication a little bit more secure. But the underlying HTTP is fundamentally the same. Underneath the application layer, still running on your computer, this would be something that maybe your network card would do. So whether you're using Wi-Fi or an actual wired connection, doesn't really matter yet at this point, is what's called the transport layer. Okay? And so what the transport layer tries to do is move messages from your network interface, whether you're using the wired connection or a Wi-Fi connection, whatever packets or whatever messages need to be sent, the transport layer collects all of the messages that your applications are sending and sends them out. And then it receives all of the incoming messages and routes them back to the appropriate application. So for instance, suppose you've got running on your computer at the same time an email client, a web server, and you've got the Netflix app running because you're streaming, I don't know, what just came out, Stranger Things. Okay? Are all three of those applications using the internet simultaneously? Sure. But does the Netflix app need to know anything about Chrome that's running, and does Chrome need to know anything about the email server that's running? No. In fact, good design would say they shouldn't need to know about each other. The transport layer is then what says, well, when Chrome sends a message saying we need a web page, the transport layer connects that and handles how does that actually get pushed into the network and into the internet. When a packet comes in, when a message comes in from another machine, the transport layer says, oh, this message was intended for Netflix, and routes the message to Netflix on your computer as opposed to sending it to the email server or the internet browser, again, depending on what the nature of that message was and who it was intended for. And so this is where we see that TCP. We had mentioned that a minute ago, it's Transmission Control Protocol. I misspoke a moment ago. That's where TCP comes in. That's one protocol that helps us take these messages from our network card and distribute them to the appropriate application on our computer. Does that make sense? Okay. We also have that underneath that is the network layer. So what the network layer now does is, this is where we're going to spend most of our discussion on the internet here, is actually move the information through the internet. This is where we're now saying, here's our message from one device. We need to get it to the other device. How do we do that? Okay? Because we've got this network that we need to move all of this information through. And so now, there's no application context. All the network layer knows is, where did the message come from? Where is it going? Okay? All of that application context to say, well, this is a website, or this is streaming video, or this is an email, is in that message, but the network layer doesn't care. You know, think of it as UPS. Does UPS care what's in the package before they deliver it? Okay, so long as they know it's not hazardous and it's not explosive and all of that, do they care? No, they just take the package and they deliver it. Same thing going on with the network layer here. Doesn't matter what the data is. It'll deliver it. And the protocol that we end up using here is IP. It's our internet protocol that we mentioned a few minutes ago. Getting now down into the nuts and bolts of hardware, underneath the network layer we have what's called the link layer. And so this is where we sort of fundamentally actually move the data from one device to another device. So you could think about this as being like Ethernet. This could be maybe your Wi-Fi connection where we're actually moving the data around. Okay, this is, and going into detail on this requires actually getting into a lot of computer engineering. We're not going to say much more about the link layer. And then there's the physical layer where now instead of moving data, we now consider how do we move each bit from one device to another. And so this thinks back and harkens back to our data transmission unit, where we then say, well, what are the probabilities? Is there some sort of coding that we might want to do to make sure that these bits get transmitted successfully? And we don't have very much to add to this beyond what we did a few weeks ago. Okay? But basically, so these sort of 5 layers divide up the internet into different regions where we can now sort of target how do we want each of these to work. Okay? Any questions on this? We're going to spend probably the rest of today talking about those first 3 layers. Like, so we don't have much to add to the link or physical layer from what we've already discussed. But any questions before we dive in? Okay. So basically the way the layers sort of work graphically, as we're going through this machine or through this internet, so we now have, maybe here's our source. So this is our computer, and we're going to send a message to the Stony Brook web server saying we want the Stony Brook homepage. Okay, is that something conceivable we could do on the internet? Sure. And so we come in, well, we start with our application, which is to say our web browser, where we typed in www.stonybrook.edu. Okay? Our application, our web browser, now sends the message to the transport layer saying, here's how we need to communicate using our HTTP, our Hypertext Transfer Protocol, to go get that web page, and we'll wait for it to come back. Okay, but we put our request down to the transport layer, which then marks it to say, oh, well, this goes to the computer's web browser. It belongs to that application, and we're expecting a reply. Okay, encodes all of that, and sends it down to the network layer to say we now have a message that is destined for the Stony Brook web server. Okay, at this point, we don't care what's in the message anymore, but that's what happens. We then now shove that data into the link layer and into the physical layer to actually move those bits. We do some route finding through the internet. So this now shows maybe here's a hypothetical route that we might take. Along the way, we have to pass through a switch, which is just sort of an intermediate device that just relays information on. computer engineering, the longer distances that your device has to transmit, sort of the harder it is to move the data, the more likely it is that errors will get introduced. And so we might put switches along the way to sort of serve as relays to sort of receive the data, add some more juice to it, and send the message out again. That way we don't get a lot of message degradation as we're going through the network. We can then reach what's called a router, which potentially has the choice to route the message. So a router comes in, and now we go back up to the network layer. What's the next device we have to send this message to on its path? Okay? And there might be several choices that the router has. So for instance, even though maybe you're here, if you've got your phone or your computer out, you're connected to probably WolfieNet Secure, does that mean you are directly connected to the Stony Brook web server? What do you think? If you're here, are you directly connected to it? No. You're connected to whatever the wireless router here is in the room, which is then connected to the Stony Brook infrastructure full of a whole bunch of routers and switches that are eventually connected to the web server. And so most of our route finding is then how do we get through the routers and all of these devices to get the message from A to B. We'll talk about that. That'll probably be most of the focus a week from today. And then finally, our message gets received by the Stony Brook web server per se, goes back up through the layers, so the network layer gets it, sends it up to the transport layer, which says, oh, this is a message that's designed for this web host server. Send that up to that computer's application, which is to say the Stony Brook web server. They receive the message saying, send us stonybrook.edu, the homepage, and it responds back and says, oh, sure. Puts a message together, puts the message back into the transport layer to send it to the network layer to go sort of back through and send that web page back to us, where then we receive it after going through this whole network, back up here, and eventually it comes back up to our application layer, which receives that message and then displays the home page. Okay? So there's a lot going on underneath the hood every time you hit enter on your web browser. Okay? Questions on that? Great. So why do we spend all of this time and why do we divide up the internet into these layers? This seems sort of really complicated. Well, the answer is the internet is really complicated. And so why do we do these layers? Well, for one, it's something of a good problem-solving strategy. As we saw in our algorithms unit a little while ago, if we've got a really complicated problem, sometimes it might help to break it up into things that are maybe a little bit smaller or a little bit more manageable. And so the idea is maybe we can do that and start to then focus and isolate different parts of the internet and approach each of them independently and try to do each of them really well. The other idea then is suppose a better protocol is developed for one layer. We come up with a better way to actually do the transmission control, that TCP. Do we have to then rewrite the entire internet? No, we just have to change that one layer. We have to update our network cards on the computer, which might take on the order of 10 years to do for everyone to sort of their old computer to crash and they finally go buy a new computer that's using the new one. But is that much easier to do than replacing the entire internet? Yeah. If a new wireless protocol comes out, we have to update the link layer. Does our web browser care that suddenly we're using a better wireless network? No, our web browser doesn't care. It just says we need to put a message into the internet. What happens with it from that point, not my problem. We're just going to assume everything else is working. And so as technology gets better by having these layers, it makes it much easier to improve one layer and swap things out for better technologies and better protocols that might be developed by any one of you. Okay? So now let's dive in and look at these three layers with maybe a little bit more detail. And so we'll start at the top of this application layer. And as we said before, the goal of the application layer is we want to take whatever processes that you're doing as the user, whether it's email, streaming things, web surfing, whatever the case may be, online gaming, I don't know. And we need to convert your actions into protocols that the internet can understand so that these devices can communicate. And there are several. We've already mentioned HTTP. So this is what's used to do web pages and usually the associated data for web. So like any images that are embedded or any fonts that are embedded on a website will all get transmitted through HTTP. Okay? Another one that's used, there's something called the File Transfer Protocol, or FTP, which is more just for just unspecified data. You've just got a big block of data, want to move it somewhere on the internet. You can use the File Transfer Protocol. There are also several different protocols for doing messages and email. One common one that is used is what's called SMTP, or the Simple Mail Transfer Protocol. Again, that's specifically designed for handling email. Okay? This is by no means an exhaustive list. Pretty much every time you're going to do something different on the internet with an application, there's going to be a new protocol invented to then structure how do we do this communication to move this data around from one machine to another. So maybe to discuss HTTP a little bit more, how does the hypertext transmission actually work? So as we saw in that example a moment ago, what will happen is we take our computer and we're going to need to open a connection with whatever the web server is. So we're going to send a simple message saying, hi, I want to communicate with you. And that machine is going to acknowledge back and say, hi. Communications are open. We then send our request saying, we would like to have this particular web page, or this particular file, or whatever the document is that we're requesting from them. And then it's going to come back and it's going to send the file. Notice now this is a much bigger message because it's not just some simple little request. It's actually the entirety of that file per se. And it's going to send it back and we get file received. Now, something that the HTTP also includes are different codes for doing error diagnosis. So, how many of you have ever seen an error 404 on the internet? Okay, every hand goes up. What does 404 stand for? Page not found. So what happens? So you initiate the connection. Server says, hi. And you then say, I'm requesting pagethatdoesn'texist.com. Okay, well, does the other server know how to send pagethatdoesn'texist.com to you? No, because it doesn't exist. And so rather than just sending you some junk, it will send you politely. Again, protocols are all about how do we communicate politely. It's going to send you a message with the status code that says 404. I don't know what you're talking about. I don't have that. I can't provide it to you. Perhaps you should try again. Okay? And so it'll send a message back with error 404 saying, I don't have that. Other common messages that you might get, has anybody seen a 403 error before? Maybe a handful of people. Usually this comes when the website requires you to log in or have some sort of credential to view what's going on. If you don't have the credentials, the web server will send back a 403 saying permission denied. You are not authorized to see that web page. Okay? So if Blackboard times out, it's usually a little bit nicer where Blackboard itself will actually just create a web page that says you do not have credentials. This is on a much more base level. Yep. 403 errors anymore are fairly rare. Most websites and web servers are developed enough that they would have their own page to sort of politely say, oh, you need to go log in or you're not authorized to view this, as opposed to, you know, Chrome's just very bland, error 403, permission denied. Okay. Other ones, has anybody ever seen an error 400? These are very uncommon. What this says is maybe something got garbled. So along the way from where you sent your request to when the machine received it, something got garbled in the internet or your internet browser malfunctioned and made a bad request. And now, unlike the error 404 where the receiver said, oh, you want this web page and I don't know what you're talking about because I don't have that, this is now the server saying, I don't know what you're asking for. Okay? And so it would then send back a message saying error 400, can you maybe send that again? Okay. Most web browsers today, if they get a 400, will actually resend the request. Okay. Rather than sort of displaying to you that there's an error 400, it'll keep trying to send it to form that data. And then the last one, has anybody ever seen an error 200? It's a trick question because 200 means there's not an error. This is what the website will do. So part of the HTTP, it always includes a code, a diagnostic code. 200 means, oh, I received your request, I found the file, it's attached, have a wonderful day, goodbye, click. So does your web browser actually display error 200? No, it just displays the web page because it got what it asked for. There are plenty of other error codes that go in, but again, this is designed to help give you some diagnostic information. When something doesn't work right, what went wrong so that we might try to be able to fix it. Okay? Oop, wrong way. So, one of the other questions that we then have to have for the application layer, and this sort of straddles into the transfer layer and the network layer as well, but thinking back to our data storage unit, how do we actually do web addresses? So we've been talking all of this time that there's stonybrook.edu. Is that something a computer can understand or work with? Maybe not directly. Remember, back from our unit on data storage, computers only process sequences of zeros and ones. Is www.stonybrook.edu a sequence of zeros and ones? No, it isn't. So how can we actually think about web addresses and locations when we're used to working with URLs and other websites, when the computers want to work with things that are zeros and ones? How does this work? Okay, well the answer is, and we've already mentioned these ones today, we use this thing called IP addresses. Okay? So you could maybe assume, well, don't necessarily assume this, but you could perhaps verify, Google.com may have an IP address that looks something like this, where now we're going to get 4 numbers. All of them are between 0 and 255 inclusive, which is to say 2 to the 8th. There are 8 bits dedicated for each of those numbers. And we can identify those 4 numbers now as our address. So now one of the things our application layer or our transfer layer or our network layer, again, this sometimes it's garbled between those different layers, how do we convert Google.com into that IP address to know that as far as the computers are concerned, Google is 167.206.13.180? Anybody know? Nope. So what we can use is there's this piece of technology called the domain name system. You might have seen, again, if you've ever had to troubleshoot anything on the internet, the acronym DNS. Anybody seen DNS before on the internet? Okay. This is what this stands for, and this is the way of how do we take a name that is human readable, like Google.com, and associate with it the actual IP address to identify to the computers and to the network where is that server, where is that device. Okay? And so there are different tools that you can use available to you. So one is called NSLOOKUP, where you can actually put in a URL, and it will try to find for you what is the IP address of that. So let's actually escape out of here. The way to do this, you need to pull up a terminal. So on Windows, you can usually go to like the Start menu, Accessories, Command Prompt. If you go like on a Mac, you can just search for Terminal, and it'll find it's usually in the Accessories folder or the Utilities folder in your Applications folder. If you're using Unix, you already know what a command prompt is. And pretty simply, we can just type in NSLOOKUP, and if I spell it right, that would help. And we can put in a web page, and it will go, and it'll run. And so first thing it does is it comes out. So first of all, there's a request that timed out. It tried to find this, and it couldn't at the very beginning, so it tried again. The first things that's going to show up for us is, who are we? Okay, so it tries to give us server, which in this case it doesn't know because Windows is stupid. I'm not a Windows fan, by the way. I'm actually very bitter this morning that I'm having to give this lecture on a Windows machine. And then it gives our address. So the IP address of this computer that's projecting the slides right now and all that is 10.1.16.16. Is that to say, is that the IP address of Google? No, that's us. So now what it does is it comes in and says non-authoritative answer. We'll come back to the phrase non-authoritative here in a moment. Name Google, and then it gives the address both in hexadecimal and in the IP format, where now we see that Google is 172.217.13.228. So when you want to go visit Google.com, or at least on this computer, go to Google.com, it will convert that into 172.217.18.220 or .13.228, which is something that the computers can use to help find this and route these messages around. Okay? We can put in plenty of other websites here if we wanted to, but that's the idea. There's a tool here if you're ever curious what are the IP addresses. What would happen? I'm curious to run it a second time. Okay. Notice this address here, this 172.217.13.228, is not the address that we had on the last slide. Where is it? Full page. We had something different. Sometimes if you run on different computers and at different times, these IP addresses might change. Okay? One reason, especially since we're using Google as an example, does Google have one server located in California that handles all of its traffic? No, it's got lots of servers all over the world. And so depending on which computer you're on, how you route through, because there's that word, that non-authoritative, might it find different access points to Google? Yes, which could have different IP addresses. And so like when I was preparing these slides on my computer a while ago, Google actually was 167.206.13.180. That might still be Google, but it would be a different Google server than what this computer was able to find here in lecture. Okay? So, coming back to the idea, it said it was a non-authoritative answer. Why do you think it's a non-authoritative answer? When we were looking for how do we convert that URL into an IP address? Well, one of the issues, if it was going to be an authoritative answer, what would we have to have? Don't overthink this question. We need an authority. We would need to have some centralized repository where there are all of the URLs and all of the associated IP addresses. Such a thing doesn't exist. So, in the absence of an authority, can we even have an authoritative answer? No. So what do we do then instead? Well, what we're going to find out is that the DNS servers are very decentralized, meaning that there's no one server with a complete authoritative index of all websites and IP addresses. What ends up happening is there's about 13 root name servers worldwide. You'll see quite a few of them are located in America. There's a couple in Europe, and there's one over in Japan. There are certainly lower level servers that handle more regional things. Maybe the Northeast has probably several of them. The Midwest has one. I'm sure there are a couple in like Mexico and Latin America and Central America. South America has a couple. Africa has a couple, and so on and so forth, a little bit more geographically. But we can sort of decentralize these things. And why might they be decentralized? Any ideas for why we don't have one big authoritative DNS server? What was that? I still didn't. Because it could overload. Okay, how many different URLs are there and IP addresses to store? Probably billions, if not more. That's really a lot for one server to hold. Number two, if there was exactly one server, how busy would that server be? If every time someone anywhere on the world entered a URL into a web browser, and that one server had to get contacted to figure out how do we convert that to an IP address, that server is going to crash before anything gets done. Okay, so from a practical application, we just can't have one. There's just too much demand for what that server is doing. So that's one reason. Number two, there's just so much that it would be impractical. And there's a third reason that sort of comes into question here that has nothing to do with computers per se. Not necessarily even the location. I mean, we can put these things anywhere we want. We've just sort of arbitrarily chosen some of the locations drawn here on the map, usually based on where was their big university or government facility that helped develop the internet back 20, 30 years ago. But one of the issues, if we want to get really cynical, who do we trust to maintain that index? If there was one person, one server maintaining that index, and they suddenly decided, oh, I don't like Google, they're not being very nice to me, could they make it that Google basically becomes unreachable on the internet? Yeah, because they could just say, I don't know. You go to them and say, I want to know where's google.com, and they're like, I don't know, there is no google.com. Do we trust one person to wield this much power and this much information? No. So if we decentralize it where then everyone is sort of running their own server, if you don't like the answer you get at one place, what do? Go ask someone else. You go ask Mom, can I have a cookie? She says no. You go ask Dad. Okay? And this is the case where Mom and Dad aren't coordinating, and Dad probably is going to say yes. And if he doesn't, then go ask Grandma. Grandma always says yes to cookies. Okay, so, but that's sort of the idea is, number one, it's just impractical to have one server, but number two, we don't trust anyone to maintain it. Okay, and so we have all of these servers worldwide all sort of working together. I don't think there's anyone being particularly malicious. I have no reason to believe that they are, but we do have sort of this safeguard in place to prevent one person from trying to blacklist something on the internet. Okay? Any questions on that? So basically, again, this sort of sums up our application layer, but the idea is whatever program we're using tries to convert whatever you're doing into some sort of message that can be put on the internet. And part of that is how do we deal with these URLs to domain names, how do we store addresses, things like that. Okay? That's all sort of part of the application layer. Moving on, our next layer is the transport layer, which starts to put together, there could be multiple applications running on one device at any given time. So for instance, how many of you, I see several computers out right now, have multiple tabs open in your web browser? Okay. Those of you that don't have your computer, how many use multiple tabs on your web browser? Okay, every hand goes up. Yep. How many of you ever at the same time run a web browser and an email client? Or a web browser and a streaming service? Or a web browser and a video game that uses stuff online? Okay, there's hands going up. The point is, almost at any given time, you're probably using more than one application that's accessing the internet. And so the key idea of the transport layer is when we need to send a message into the internet, we need to know which application did that message come from and how do we make sure it gets routed. Because maybe there's 15 applications running on your computer. How many interfaces to the internet does your computer have? Usually just the one. You've either got an Ethernet cable plugged into the computer and you're using a wired connection, or you're using wireless. And so how do we now, from a sending perspective, how do we condense all of those applications, whatever they're trying to do on the internet, into that one stream to funnel into the internet? And then likewise, when we receive the messages from the internet coming in, how do we distribute them to the appropriate target? How do we know that this message contains a website, and that's destined for the web browser? This message contains an email, which should go to the email server, or the email client. This one contains the next set of instructions for the video game that you're playing to make sure that, whatever it is you were doing on, I don't know, what's the World of Warcraft? I'm not an online gamer, sorry. That you get the new instructions or the new video routed, or the message from your friend saying, if you don't heal me now, I'm going to die, you jerk. Okay, that's what the transport layer does, which is what we just said. And so one of the key things that comes up, and again, think back to our data transmission unit, where we said, well, we looked at, here's a total message we need to send, and how many errors were maybe introduced. And one of the ideas that we came across was to say, well, what if we broke our message up into lots of smaller pieces? Did that help it get through the network better? Sure. And then we saw if we had small enough pieces, we could use these error correcting codes. Like if we had just these 4-bit messages, we could turn them into these 7-bit things where we could correct for errors. Sure. We're going to do a very similar thing now, where what the transport layer is going to do is take whatever message your application is sending, and it's going to break it up into discrete chunks called packets. Each packet, it depends sort of on the specific implementations, but usually maybe like a kilobyte in length. Stuff like that. Some might be a little bit bigger today. And so, number one, what this does is it allows better diagnostics when something goes wrong. So again, what the idea is, if we broke our total message up into little pieces, if we know that piece 4 had an uncorrectable error, do we have to resend the entire message? No, just resend piece 4. Okay, we can assume that pieces 1, 2, 3, 5, 6 were received okay. We didn't get any error messages on it. Okay? So we can do the same thing. So this sort of minimizes duplicate communication through the internet. And then it also allows us to sort of add some of this other information in this context to know which application these different packets correspond to. Some of the protocols that the transport layer uses also try to prevent too many packets from being generated at a time, which might clog the internet. Those of you that are maybe a little bit more into online gaming or tech things probably know the term denial of service. Anybody heard of that before? Or a DOS attack? DOS for denial of service. Anybody know what this is? You're nodding yes, so now I'm going to pick on you.
It's like a lot of people try and go on the same exact server or something at the same time, which causes it, and then it takes it down.
Right, so the idea here is, there's going to be one person or several people, but someone's maybe trying to be a little bit malicious and take down a server. So they just start sending lots and lots and lots and lots and lots of messages at that server, to the point that that server, wherever it is on the internet, can no longer keep up with the messages that are coming into it, which basically blocks it from the internet, because if none of the messages are getting through and getting processed, it's functionally not on the internet. And moreover, it might actually take the server down if it overloads or something, and it could just completely crash. This is called denial of service. So you'll see, it's about once a year or so, somewhere on the internet, there's some denial of service that takes out some sort of regional part of the internet because someone targeted one of these regional domain servers. And so if we can't actually access our server that says, oh, well, Google is whatever it was, the 167.whatever.whatever.whatever, and we can't actually get that information, every time we type in google.com, our web browser is just going to hang. Because it doesn't know how to contact it. We can't get that IP address. And that basically takes down the internet when none of your URLs can get converted to IP addresses. Unless you just happen to know the IP address for Google. I wouldn't necessarily work on memorizing it. Okay? And so you'll see this from time to time. But when you see like denial of service, that's what's going on. Someone's just flooding lots of packets. And as it turns out, some of the protocols that are used in the internet try to prevent this from happening and try to recognize, is someone trying to clog the internet, or there's a certain rate at which you're allowed to put packets in to try to make sure everyone's playing nice and fairly. Okay? And so one of the other interesting things that can happen on packets is that, so we take our total message from the application, we break it up into all of these different parts, and we're going to number them so we know, this is part 1, part 2, part 3, part 4, part 5, etc. We're going to probably send them in order. Okay, so as our transport layer is now putting these messages into the internet, first we put in packet 1, then we put in packet 2, we put in packet 3, and so on and so forth. Does that mean that the packets are received in the same order on the other end? What do you think? Is that something that's necessarily going to happen? Would it be nice if it happened? Sure, it'd be great. Does it happen? Probably not. Okay. One of the things that we'll see when we get into our discussion of the network layer in a few minutes and then mostly next week is that it's not even guaranteed that 2 packets, they can be for the same application thread. We've got packet 1 and packet 3. They're not even necessarily going to take the same route through the internet. We want to go to stonybrook.edu from here. One packet might just go over to the admin building or wherever it's stored. The other one might go to China on its way. That's a really exaggerated example. But it's possible. Okay? So there's absolutely no guarantee that the packets are received in order. So one of the things that the transport layer is going to do on the receiver's end is we're going to know, well, this application had to send this message. How many total packets were in that message? And until we receive all of those packets, do we forward the information up to the application layer? No. We got to sit on it until that message is complete. So number one, they might be received out of order, so we can put them back in order by knowing, well, we should have packet 1, then 2, then 3, then 4. And we have to make sure that we've received all of them. Otherwise, you just get sort of an incomplete message going up to the application layer, which then might give you part of a web page, or part of the streaming video that you're watching, or part of the email saying, dear class, there's been an emergency and your exam time has been moved to end of message. I'm sure you would love getting that email. Everyone's blood pressure starts going up just a little bit. Okay? But that's what the transport layer does, is take these messages from the application layer, break them up into pieces, send them into the internet, and then when it's receiving them, receive all of these pieces, all of these packets, put them in order, wait for all of them to arrive, and forward them back up to the application layer with whatever message was put in them. And so that brings us now to the network layer, which is where we're going to spend, well, certainly the rest of today and most of the next class period looking at, which is to actually say, how do we route the information from one device to another? So now we've got whatever this packet is. We don't care what application originated from. We don't care how many packets were part of that total message. We have this packet, and it needs to start at our machine and go to stonybrook.edu. Okay? How do we get it there? And so this is now, as we've already mentioned, what did our Google Maps and the internet have in common? Well, now we can maybe amend our driving question. How do we determine the best route between 2 devices? So we now have this internet. There's all of these different computers and routers and packet switches and servers and cars and wireless stations and all this. How do we get the device from point A to point B? And that's what the network layer really focuses on. And so what we're going to end up doing, essentially, is thinking now, as we alluded to at the very beginning, that the internet is this big graph where we have all of these different devices on the internet, whether they're computers, routers, wireless routers, laptops, servers, cars, cell phones, whatever. We've got all of these different devices, and we can make a graph. So a vertex on our graph is going to be what? It's just going to be some device. And what's the edge going to be on our graph? Or what are the edges going to be? Some connection between them. So we know there's a direct connection. This computer has a wireless connection up to whatever the wireless router is. Okay? So there would be an edge drawn between this computer and that wireless router. That wireless router is probably connected to your phones and to your computers if you have them out right now. Also edges then from that wireless router down to those computers. But that wireless router is also connected to some other router and the rest of the campus internet infrastructure, which is connected to our regional internet service provider, which is connected to a global internet service provider, which is then connected to other regional internet service providers, which would be connected to some server in Copenhagen. Okay. So we get this whole hierarchy of things as we've got sort of symbolically pictured here on the left. The other thing that we're going to have, just as we had with Dijkstra's algorithm and with Google Maps, is there's going to be some cost to doing each function. Okay, so I want to send data from this computer here to stonybrook.edu. There's going to be a cost for sending my message on that wireless link from this computer to the wireless router. Now, is that cost in this case unavoidable? Yeah, because this computer is not hooked up to any other internet. We'll ignore the Ethernet cable here running around. Okay? But so that's unavoidable. But then once it gets to that router and into the broader internet infrastructure, how many possible routes are there for us to go? Probably quite a few. And what's ideally the cost of any one of those routes? Do we want a path that has a high cost or a low cost? We want a low cost. I mean, the internet's free, but that doesn't mean it doesn't cost anything. That's why you have to pay, I don't know, what is it, optimum $70 a month for internet service? Something like that? Okay? That's to maintain all of this infrastructure and keep it working. Okay? And so cost, just as we have with Dijkstra's, there's not a unique way to define it. So whatever it is, we're going to have to set up some sort of cost function. And now it might be a combination of what's the transit time? How long does it take the message to go between two places? What's the fidelity rate? Wireless communications tend to introduce considerably more errors than wired connections. And so if we have to spend more time doing error correction routines to make sure that these bits are correct, that might increase the cost of the connection. There might be a bandwidth issue. How much information can we put across that connection per some unit of time? If we have a high bandwidth, then that's going to be somewhat of a low-cost transmission, versus a low bandwidth might take us a really long time to get that data put through. And there's all sorts of other factors that might go in, but at the end of the day, we have some cost associated with these links. And so what we can end up doing then is making this big weighted graph out of the internet, and we can start to do this exact same procedure of route finding. Okay, so we're not going to get into the algorithm of how that works today. That'll be our focus next time. But before we end, what we can do is there's some other neat tools that you've got already installed on your computer to help you find out how these routes work. And one of them is called Ping, which tries to address the question, how long does it actually take a message from your computer to reach some other device on the internet? Okay? And so we can try to ping Google. So if we come in here and do ping google.com, we can come in, and so what this is doing is Ping is just going to create some packet. There's probably nothing in it, just saying, this is a ping, just send it back. And what the server knows is, oh, it received a ping. What that says is, I send you a message, send it back with a timestamp. And our computer measures how long did it take from when we sent the message into the internet to when we received the acknowledgement from that server. And so it's going to do this a couple times. And so we see, well, here's our Google server. So it had to go do that NS lookup to see that Google was 172.217.9.238. Notice the IP address changed in the last 30 minutes. Someone updated their DNS server. And we sent the 32 bytes, and it took 4 milliseconds for that first round-trip connection. It took 4 milliseconds for a second round-trip connection. The third one, it actually took a little bit longer. It took 7 milliseconds to get to Google and back. And then 5. And so what it'll do is it'll average it. It says we sent 4, we got 4 replies. It's possible you might lose packets. It does happen in the internet. It'll show you the statistics for that. And then the average time that we got, it was about 5 milliseconds for a round-trip message for us to Google. Something that might be interesting is we can try to Google, or not Google, but ping something else. So let's do ku.dk. So does anybody know what country DK's extension is? It's Denmark. KU is the University of Copenhagen. I have friends there. And so one thing that we'll notice now is when we go overseas, what happened to those transit times? They shot up quite a bit. I'm going to ask the leading question now, but this is something that we put in the homework for you. Why do you think that time might have gone higher? Anyway, I'll let you explore that on the homework. But there's that, and there's one other tool that I just want to show you real quick here. And there's also a tool called Traceroute, or it's abbreviated to TraceRT if you're on a Windows machine, that actually is going to try to track the path that your packets take as they go through. So if we were to do now on the Windows, we have Traceroute. .com. And so it's going to try to send now, it's going to send a packet out. But now, instead of just saying, we'll send the reply when it actually gets to Google, it's going to tell every device along the way, send a reply. And we can try to see how long it's going. So whatever it tried on the first one, no one bothered to respond. The next one took about 2 milliseconds round trip for 10.1.0.46 to respond. Do you have any idea what 10.1.0.46 is? It's some device between us and Google. It's probably some router somewhere. And so we're starting to see other devices coming in. It's showing us average times. Interestingly, it took less time to go to device 4 than to device 3. something weird happened on the internet with the different routes that are going on in real time. But we can actually try to go, and this is running a little bit slow right now. I would have expected Google to be a little bit faster than this. At some point, in a lot of cases, especially like when we get to the end and we actually hit Google, it'll try to go, so like there is what eventually became Google. It tries to actually convert the IP address back to something readable, and it turns out that the local Google server that we were accessing is also registered as 1GA34S11-IN-F14.1E100.net. So remember that the next time you need to access Google. Okay? But it'll try to convert them back to URLs, but a lot of the devices in between aren't actually going to be registered because they're just servers or routers or something like that. Anyway, have a delightful Thanksgiving. Have lots of good food. Enjoy the time off. And we will pick up our discussion and finish up the internet this time next week. Have a delightful break.